Imagine yourself atop a secluded hill where a breathtaking panorama unfolds. The sky, like an artist's canvas, ignites with a symphony of colors as the sun first appears above the horizon. This daily spectacle, when the heavens are painted in warm hues of orange, scarlet, and pink, is often taken for granted as something self-evident. However, this magnificent sunrise is merely the final chapter in light's long and fascinating journey. If we trace the path of these photons from their endpoint in your retina, through Earth's atmosphere, across the 150 million kilometers of cosmic void separating our planet from its parent star, and further, through the diverse and turbulent layers of that star, we discover the true source of the warmth caressing your face and the picturesque colors that paint the sky. The sun's core is a colossal nuclear engine that has been relentlessly operating for 4.5 billion years. This luminous sphere of incandescent plasma, born in a cosmic nursery from the remnants of ancient stars and dominating our sky, is the result of a complex interplay of forces that have acted over countless millennia. But what do we truly know about this vital element of our existence? What profound processes govern its colossal power? What are its most striking features, and how do scientists delve into its depths to uncover its intimate secrets? In this overview, we will embark on a deep dive into the interior of our sun to uncover the secrets hidden behind its dazzling veil of light and time. Where should we begin our journey? Just as we enjoy a fruit by starting with its outer layers and gradually moving towards the core, we will begin our exploration with the outermost layer of the solar atmosphere, the corona. The image presented was captured by the Solar Dynamics Observatory, a space mission by the National Aeronautics and Space Administration, launched in February 2010. The Solar Dynamics Observatory was created to deepen our understanding of solar variations that affect life on Earth and our technological systems. It studies the dynamic surface and atmosphere of the sun across various electromagnetic ranges. By observing light beyond the visible spectrum, specialists at the National Aeronautics and Space Administration have been able to highlight normally invisible details that are crucial to our understanding of the sun. This image was captured using a wavelength of 19.3 nanometers, which corresponds to light in the extreme ultraviolet range. At this wavelength, corresponding to a color temperature of 1 million Kelvin, we can clearly observe the upper region of the solar corona. Remarkably, the solar corona can be seen with the naked eye on rare occasions, such as during a total solar eclipse. When the moon briefly aligns perfectly between the Earth and the sun, the central, brighter disk, known as the photosphere, is completely blocked, revealing the glowing outer layer. And while this is a captivating sight in itself, the corona still does not show the same detail as in this image obtained by the Solar Dynamics Observatory. This is precisely what makes it a valuable tool for scientific research. But let's delve a little deeper into the features of the sun located directly beneath the corona. At a color temperature of 20 million Kelvin, intensely bright spots indicate phenomena known as solar flares. Here are clips from a particularly active week of flares in August 2022. Solar flares have always appeared simultaneously terrifying and mesmerizing. These are colossal explosions during which the sun ejects enormous amounts of electromagnetic radiation. They occur when magnetic fields intersect, deform, and undergo rapid reorganization. This activity is a result of the turbulent nature of the plasma within the sun itself, from which these fields ultimately form. Solar flares and coronal mass ejections are high-energy phenomena comparable in scale to millions of nuclear explosions occurring simultaneously. The magnetic reconnection events that cause them can lead to the expulsion of vast amounts of radiation in the case of solar flares and matter into surrounding space. During coronal mass ejections, millions of tons of charged matter erupt from the sun at speeds ranging from hundreds to thousands of kilometers per second. However, this is not the only feature of the sun's atmosphere that generates radiation. Coronal holes, denoted here by a darker area on the sun, represent another fascinating feature that we will examine in more detail using extreme ultraviolet radiation. Studying the Sun in the ultraviolet range reveals astonishing details of its activity. Coronal holes are areas with cooler and less dense plasma, where magnetic field lines do not loop back to the star's surface but extend into space, encompassing the entire solar system. It is through these holes that solar wind particles escape unimpeded into interplanetary space. When streams of solar wind reach Earth's magnetosphere, spectacular auroras ignite in the polar regions, coloring the night sky. Ultraviolet radiation allows for a more detailed study of these amazing phenomena in the outer layers of the Sun. The invisible spectrum of light is a powerful tool for investigating the diverse processes occurring in the solar atmosphere. For example, solar filaments, also known as prominences, are gigantic loops of plasma that rise above the Sun's surface. These formations are so large that our planet appears as a tiny speck in comparison. Prominences can extend for hundreds of thousands of kilometers into space, forming in just a day, and stable structures can exist in the corona for several months. The video presented shows a prominence twisting as it rises from the photosphere into the Sun's atmosphere. Although the recording time is accelerated and minutes are compressed into seconds, the scale of the prominence allows us to appreciate the speed of matter movement under the influence of the Sun's powerful magnetic fields. A little-known fact about the Sun's atmosphere is that it sometimes experiences precipitation. Not all charged plasma ejected into the solar corona leaves the solar system. Some of it is trapped in the corona, cools, and falls back to the surface as a glowing rain. This spectacle is certainly beautiful, but it is best observed from a distance as the temperature of this rain reaches millions of degrees. However, only a portion of the solar plasma is destined for a gentle return to the Sun's surface. Here, the analogy with Earth is inappropriate. Unlike terrestrial clouds, which do not tear apart like a snapped rubber band, solar clouds, held by tightly twisted magnetic fields, are capable of doing so. A slow-motion capture of a coronal mass ejection shows a structure forming in the lower left part of the Sun, which then ruptures, ejecting billions of tons of plasma into the solar system. Even with Earth's magnetic field, a powerful ejection can damage satellites and power grids. All these structures were captured by the Solar Dynamics Observatory, or SDO, using a 30 nanometer wavelength of light, corresponding to extreme ultraviolet. Time plays an important role in observing these phenomena, as they occur with varying frequencies at different periods. The Sun's activity, which determines the frequency of these structures, changes in accordance with the 11-year solar cycle. But that's a topic for another discussion. It's worth noting that using different wavelengths of invisible light can provide valuable information. For example, consider two images of the solar corona taken at the same time but using different wavelengths. The first image, taken at a color temperature of 600,000 Kelvin, shows a calm corona with coronal loops. The second image, taken at a color temperature of 2 million Kelvin, reveals hotter, active regions of the corona. This comparison highlights the importance of using various approaches when studying a star. What at first glance appears to be a single solar phenomenon may turn out to be a complex and interconnected chain of events, and we haven't even delved into the Sun's atmosphere yet. Moving inward, let's look at another image captured by SDO using a 160 nanometer wavelength of light, this time in the transition region. The transition region is the layer between the solar corona and the chromosphere, the lowest layer of the solar atmosphere. This layer is very thin, about 100 kilometers thick. In this region, the Sun's thermal temperature sharply increases from approximately 8,000 to 500,000 Kelvin. For comparison, the temperature of erupting lava in Hawaii is 1,170 degrees Celsius, or 1,443 Kelvin. Thus, the temperature at the bottom of the transition region is almost 6 times higher, and at the top, it's more than 346 times higher than the temperature of lava, 346 times higher. Delving deeper, we enter the chromosphere of our star. This atmospheric layer, captured in ultraviolet light with a wavelength of 170 nanometers, is the last frontier before the Sun's very surface. The chromosphere's thickness is estimated to be approximately 1,700 kilometers. A careful examination of this layer reveals astonishing formations known as spicules. Like tall grass swaying in the wind, these powerful jets of plasma erupt from the star's surface at speeds up to 100 kilometers per second, which is almost 282 times the speed of sound. They can reach lengths of about 10,000 meters, which is more than 1,000 meters taller than Mount Everest. Forming and disappearing in an average of 5 to 10 minutes, the nature of spicules remained a mystery for a long time. Scientists debated how magnetically charged particles could escape the sun's magnetic fields at this level. The enigma was solved in 2017 when a group of researchers working on a detailed model of spicules discovered that their origin was linked to neutral particles. Initially, scientists did not consider their influence, believing they had no significant effect on the movement of magnetically charged particles. However, once neutral particles were added to the model, it was found that they provided magnetically charged particles with the unexpected buoyancy needed to escape the solar plasma and form spicules. Continuing our descent through the lower layers of the atmosphere, we reach the photosphere, the sun's very surface, which we see in visible light. Although the edge of the photosphere appears sharp and smooth, this is merely an illusion caused by the immense distance to the star. In reality, the sun is not a solid body at all. Due to the extremely high temperature at which matter cannot exist in solid, liquid, or gaseous states, the sun is composed of plasma, the fourth state of matter, estimated to constitute 99.9% of all matter in the universe. Plasma is similar to gas in many ways, but consists of a mixture of ionized atoms and free electrons. The photosphere, about 400 kilometers thick, is the outermost layer visible in images. It's important to understand that this is not a fixed, solid boundary of the sun, as it may appear at first glance. Unfortunately, this is the deepest layer of the star that scientists can directly measure. Looking closely, you can see dark spots on the left side of the image. These are sunspots, which appear darker than the rest of the photosphere due to their lower temperature. However, this difference is only noticeable when compared to the incandescent surroundings. Unlike coronal holes, sunspots form in areas with particularly strong magnetic fields. In these areas, heat is trapped beneath the photosphere due to weakened convection. Comparing this image of the sun with the previous one, taken in extreme ultraviolet light during the same period, reveals a connection between sunspots and flares. The spectacular solar flares and sunspots coincide in location. By studying the processes occurring beneath the surface, it becomes clear that one phenomenon is the cause of the other. Sunspot sizes vary from 15 kilometers to 160,000 kilometers, several times the Earth's diameter. Let's examine some of these sunspots in more detail. This image was captured by the Swedish Solar Telescope, located on Earth, using visible light with a wavelength of approximately 400 nanometers. Near and around sunspots, the photosphere is filled with jagged, constantly changing cells reminiscent of cooling, cracked lava. However, these cells, known as solar granules, reach a width of about 1,000 kilometers. They can be imagined as the top layer of a churning convective cell located below. The brighter areas within each granule represent flows of unimaginably hot fluid rising from the sun's upper interior layer to its surface. Upon reaching this boundary, the fluid is forced to spread outwards. Gradually cooling, the fluid sinks back inward through the rough, dark boundaries surrounding each cell, and the cycle repeats. This process is very similar to the convection currents in Earth's mantle that drive tectonic plate movement. This process is by no means trivial. Although each granule exists for only about 20 minutes on average, the flows of matter within these cells reach supersonic speeds, exceeding 7 kilometers per second, generating waves on the sun's surface caused by sonic booms. Notably, these granules can be distinguished even in a full-disk image captured in the visible light range. At first glance, the image might appear grainy for a spacecraft equipped with advanced technologies, and it is indeed. However, this graininess is nothing other than the granules on the sun's photosphere, not processing artifacts or excessive noise. Unfortunately, our journey into the sun's interior ends here. as scientists have not yet developed methods to image deeper layers using both visible and invisible light. Much of what lies beyond this layer remains a mystery. Nevertheless, we recognize the immense benefit that using different spectra of light brings to studying the sun. Our star is constantly teeming with activity, much of which would remain invisible to us without these visualization methods, while much about the processes occurring within the sun remains unknown to us. The key to understanding often lies in studying its origin. How did the brilliant splendor of our sun come into being? To comprehend the sun's formation process, we need to go back in time, even before the emergence of our solar system, approximately 4.6 billion years ago. At that time, in a relatively calm region of the Milky Way galaxy, a vast cloud of gas and dust, known as a giant molecular cloud, drifted. This was an unusual cloud. It stretched for hundreds of light years and possessed a mass equivalent to millions of suns. Within this cloud were scattered remnants of ancient stars that had long exhausted their nuclear fuel and exploded as supernovae, ejecting their enriched elements into cosmic space. This stellar debris contained a mixture of elements such as hydrogen and helium, the primary building blocks of stars, as well as heavier elements like carbon, oxygen, nitrogen, and iron. The presence of these elements made the molecular cloud a favorable environment for the formation of new stars and planetary systems. However, a trigger was needed to initiate the cascading collapse that leads to a star's birth. Scientists believe that such a trigger could have been a shock wave from a nearby supernova explosion, which compressed parts of the cloud, causing it to fragment and collapse in regions of higher density. This collapse marked the beginning of the presolar nebula, a dense region within the molecular cloud that ultimately gave rise to our solar system. Some scientists have even proposed a name for this hypothetical exploded star, Coatlicue, after the Aztec goddess of earth and fertility, symbolizing the cycle of death and rebirth, where the death of one star becomes the seed for the formation of new ones. As the gravitational collapse of the giant molecular cloud continued, it did not lead to the formation of a single massive object, but rather to fragmentation into many dense clumps. This fragmentation process is driven by a phenomenon known as the Jeans instability, named after the British physicist Sir James Jeans. The Jeans length is a critical distance within a cloud at which gravitational forces are balanced by the internal gas pressure that supports the cloud. When a certain part of the cloud exceeds the Jeans length, it begins to collapse under its own gravity. Different regions within the molecular cloud exceed this Jeans length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse independently, forming multiple protostellar cores rather than a single massive body. The protostellar core represented the earliest stage in our sun's life, where it already resembled a star, contracting into a denser sphere under its own gravity. The core was surrounded by infalling gas and dust. As more and more matter accumulated, the core became denser and hotter, setting the stage for the next phase of star formation, the protostar. Protostars, the birth of celestial bodies. When a protostellar core reaches sufficient density and temperature, it transforms into a protostar. The central region begins to emit light and heat derived from the energy released by gravitational contraction. However, the core has not yet reached the temperatures required to initiate nuclear fusion. As it continues to accrete matter and increase in mass, the protostar experiences a sharp rise in pressure and temperature in its core. Our sun went through this stage of compression and heating for millions of years until its core temperature reached approximately 10 million degrees Celsius, at which point hydrogen nuclei began to fuse into helium. From this moment, our star was born. At this stage, the angular momentum of the surrounding matter encircling the young star creates rotation. A cloud of this size will always possess a slight rotation. Nothing in the universe is truly stationary. The law of conservation of angular momentum dictates that the cloud must spin faster and faster as it contracts into a denser space. This effect can be compared to a figure skater who accelerates while spinning by pulling their arms close to their body. Around the rotation's equator, some matter moves fast enough to remain in orbit, but above and below this, the momentum is insufficient to counteract the protostar's gravitational pull, and the matter rushes towards the center. Thus, the cloud flattens into a disk, known as a protoplanetary disk. In this disk, like a cosmic lottery, planets, moons, asteroids, and comets form and are destroyed as it cools and clumps together. Some matter loses its momentum and falls into the sun, while other parts become celestial bodies that make up our solar system today. Thanks to its ability to convert hydrogen atoms into helium, the sun gained the capacity to generate energy capable of resisting the gravitational forces that sought to compress it further. The energy released during fusion reactions creates outward radiation pressure that balances the inward gravitational pull of the gas. This allows the young star to achieve a stable state known as hydrostatic equilibrium. In this state, the star ceases to contract under its own gravity and enters a stable phase of its life, known as the main sequence. This balance between the outward internal pressure and the inward gravitational compression is the axis that defines every stage of the sun's and all stars' lives. We observed this during the initial collapse, and here, as it stabilizes into a main sequence star, and it will be the pendulum that ultimately leads to its dramatic demise. Now, we will examine the process of nuclear fusion and how it is capable of sustaining such a massive object as the sun, stable and steady for billions of years. To understand how nuclear fusion occurs in the sun, it's essential to examine the extreme conditions prevailing in its core. The temperature here reaches approximately 15 million degrees Celsius, and the pressure exceeds Earth's atmospheric pressure by more than 250 billion times. In this fiery cauldron, hydrogen atoms are stripped of their electrons, forming a plasma composed of free protons and electrons. Under such intense conditions, these protons, normally repelled by their common positive electrical charges, are forced into extremely close contact. The force that typically keeps them apart is the Coulomb force, the electrostatic repulsion between positively charged particles. This is the same force that arises when you try to push together the like poles of a bar magnet. Overcoming this force is the primary challenge for nuclear fusion to occur. Despite the enormous kinetic energy of protons in the sun's core, most collisions are still not energetic enough to overcome the Coulomb barrier. Under normal conditions, protons require colossal energy to get close enough for the strong nuclear force to act, which binds them together. This barrier is so great that physicists in the early 1920s, based on a classical understanding of particle interactions, concluded that fusion should not occur at the temperatures and pressures observed in the sun's core. To resolve this mystery, a scientific model capable of explaining many of the seemingly impossible phenomena we observe in the universe was needed: quantum mechanics. The quantum mechanical revolution of the 1920s introduced the world to a revolutionary concept that particles exhibit both discrete object and wave-like properties. One of the most striking manifestations of this duality is quantum tunneling. The essence of this phenomenon is that particles have a certain probability of traversing an energy barrier, even if their kinetic energy is insufficient to do so within the framework of classical physics. At the very heart of the sun, in its core, quantum tunneling plays a key role, allowing a small fraction of protons to effectively bypass the Coulomb barrier without leaping over it, as classical physics would dictate. Protons that lack sufficient energy to directly overcome electrostatic repulsion, thanks to quantum mechanics, are given a chance to appear on the other side of the barrier. To visualize this process, one can imagine a diagram of the Coulomb barrier. This diagram displays a high-energy barrier, symbolizing the repulsive electrostatic force that arises between two protons at different distances. The energy required to overcome this barrier is represented by a peak value. According to calculations performed from the perspective of classical physics, for this barrier to be overcome, the temperature in the sun's core would have to reach billions of degrees Celsius, which is thousands and thousands of times higher than the actual temperature. However, quantum mechanics opens up the possibility for a proton's probabilistic wave to tunnel through this barrier, appearing on the other side without reaching the peak. It is this tunneling effect that makes thermonuclear reactions possible in stars like the Sun, despite the seemingly insurmountable Coulomb barrier. Once a proton has successfully tunneled through the Coulomb barrier, it approaches another proton close enough for the strong nuclear force to take effect. This interaction, significantly more powerful than the Coulomb force, only manifests over very small distances, on the order of femtometers, where 1 femtometer equals 10-15 meters, comparable to the size of a proton. The strong nuclear force binds the protons together, but this is only the first stage in a series of nuclear transformations known as the proton-proton chain. The proton-proton chain reaction is the primary mechanism of nuclear fusion in the Sun and other stars of similar size, providing approximately 99% of all the energy emitted by the Sun. This process begins with the combination of two free-moving protons, resulting in the formation of deuterium, a heavy isotope of hydrogen, and the emission of a positron and a neutrino. This stage occurs relatively rarely, but it is crucial as it initiates a further chain of nuclear reactions. Deuterium then quickly combines with another proton, forming helium-3 and releasing a high-energy photon, a gamma ray. In the final stage, two helium-3 nuclei collide and fuse, forming helium-4, releasing two protons and a significant amount of energy in the form of radiation. While the proton-proton chain is the dominant fusion process in the Sun, there is an alternative pathway, particularly important for stars hotter and more massive than our Sun. This pathway is known as the CNO cycle, an abbreviation for carbon, nitrogen, oxygen. In this cycle, the nuclei of carbon, nitrogen, and oxygen act as catalysts, facilitating the fusion of protons into helium. The CNO cycle is more efficient at higher temperatures and contributes only a small amount to the Sun's total energy output. The energy released during these nuclear fusion reactions arises from a small amount of mass that is converted into energy according to Einstein's famous equation E = mc2. In the fusion process, the mass of the resulting helium-4 nucleus is slightly less than the combined mass of the initial 4 protons. This missing mass does not disappear without a trace, but is transformed into energy that is radiated from the Sun. Every second, the Sun converts approximately 4.3 million tons of its mass into energy. For comparison, this is equivalent to the mass of about 3 million cars being converted into pure energy every second. It is this energy that powers the Sun and provides light and heat to Earth. But before these photons, born from thermonuclear reactions, can reach Earth and the entire solar system, they must traverse 700,000 kilometers of the chaotic solar interior. To fully grasp the intricate structure of the Sun with its many layers, let's trace the path of a photon, an elementary particle of light, from the moment of its birth in a proton-proton reaction to its very exit from the star's surface. This journey is by no means straightforward. In fact, it will take this photon anywhere from several thousand to hundreds of thousands of years to complete this journey, passing through the various layers of the Sun, each with unique characteristics and behaviors. As we've learned, a photon's journey begins in the core, a region occupying approximately 25% of the Sun's radius, but containing about half of its total mass. And as mentioned, the core has a colossal density, about 160 grams per cubic centimeter, which is more than 20 times denser than iron. To visualize this, if your phone were made of such dense material, it would weigh as much as a heavy sledgehammer. For a photon, this means the environment is so packed with particles that it cannot travel a significant distance before being absorbed by a neighboring particle. Soon after, this particle will transfer the photon's energy to another particle, which will then send it on its further journey through the core until another particle intercepts it and releases it in a random direction. This is akin to trying to navigate through a dense crowd where every few steps you bump into someone and are forced to change direction. This continuous interaction of absorption and re-emission gives the core a chaotic character, making the photon's trajectory more akin to a random walk than a direct path to the outer boundary. Such chaotic movement of photons is analogous to Brownian motion, where particles suspended in a fluid move erratically due to collisions with smaller, rapidly moving molecules. In this process, there is no preferred direction in which a photon can be emitted from the particle that absorbed it. Theoretically, a photon could reach the sun's surface before randomness directs it back into the core. Adding to this complexity, as photons are continuously absorbed and re-emitted, their energy gradually decreases, transforming from gamma rays into X-rays and, ultimately, into visible light as they move towards the outer layers of the sun. Understanding the processes occurring in the sun's core presents a complex challenge for astronomers. The core is completely hidden by the sun's outer layers, precluding direct observation in any range of the electromagnetic spectrum. Instead, scientists have developed ingenious methods to study the dynamics of the processes occurring in the core. One key method is helioseismology, the observation of waves propagating across the sun's surface. Just as seismologists study earthquakes to understand Earth's internal structure, helioseismologists measure oscillations on the sun's surface caused by sound waves passing through its interior layers. The characteristics of these sound waves depend on the temperature, density, and composition of the sun's layers, allowing scientists to build models of the processes occurring in its depths. Solar neutrinos, elusive subatomic particles, are also released during nuclear fusion reactions in the sun's core. Neutrinos have such a weak ability to interact with matter that they can exit the sun in just 2 seconds, largely oblivious to the complex trajectory taken by their photon counterparts. For decades, solar neutrino detectors on Earth registered fewer neutrinos than theoretical models predicted, leading to the so-called solar neutrino problem. The solution to this mystery was only found when scientists discovered that neutrinos change their properties, or flavors, during their journey to Earth, confirming both our understanding of particle physics and the nuclear processes occurring in the sun's core. Next, the photon enters the radiative zone, extending from the core boundary to approximately 70% of the sun's radius. In this region, the temperature gradually decreases from 15 million degrees to about 2 million degrees Celsius, and the density of matter also decreases, from the density of gold deep within the zone to a density less than that of water closer to its outer boundary. The primary mechanism for energy transfer remains the process of photons creeping through the layer, transferring their energy on average to the surface. As the plasma density continues to decrease as it moves outward, the photon has more room to maneuver and can make larger jumps between interactions. But even here, beyond the core, the sun's matter remains so opaque that even a few centimeters can block as much light as hundreds of meters of water. Accurate models of the sun's internal structure have been made possible by developments such as the Standard Solar Model, or SSM for short. This mathematical framework relies on the principles of hydrostatic equilibrium, energy conservation, and radiative transfer. Essentially, it uses an understanding of material and fluid behavior gained in Earth-based laboratories to determine the properties of an inaccessible place. The SSM models energy transfer between particles in complex equations describing the movement of photons through dense plasma. This allows for the calculation of the transparency of solar material to radiation at various temperatures and densities, and for defining the boundary between the radiative zone and the next layer. Mathematics allows us to explore inaccessible environments, much like quantum tunneling allows protons to overcome the Coulomb barrier and produce the photons that are observed. Approaching the upper boundary of the radiative zone, the photon enters the tachocline, a thin transition layer where the radiative zone meets the convective zone. The tachocline represents an environment of extreme contrast, where the relative uniformity of the radiative zone meets the boiling convective zone. The unique conditions in this very thin layer likely play a key role in the solar dynamo, which generates the sun's magnetic field. The tachocline is believed to twist and amplify the magnetic field, forming the sunspots and solar flares that define the star's appearance. After passing through the thin tachocline, the photon enters the convective zone, extending approximately from 70% of the sun's radius to the visible surface, the photosphere. The temperature here drops below 2 million degrees Celsius. the sun's plasma becomes insufficiently dense to efficiently transfer energy by radiation. Instead, it becomes unstable and begins to move in massive convective currents, reminiscent of boiling water in a pot. Hot plasma rises to the surface in large cells called granules. These granules, reaching thousands of kilometers in diameter, rush upward due to their buoyancy at speeds of hundreds of meters per second, like a ball released underwater. The force required to move such a volume of matter against the sun's gravity is astonishing. The power of 10 billion hurricanes only roughly approximates the necessary energy. This convective process moves energy much more efficiently than the radiative zone, creating turbulent, rotating waves of plasma that mix vigorously. In the convective zone, the primary mechanism of energy transfer is no longer random absorption and re-emission between particles, known as radiative diffusion, but rather the upward movement of hot plasma and the downward movement of cooler plasma. This convective motion transfers energy outward more efficiently than in the radiative zone. Upon reaching the top of the convective zone, the photon enters the photosphere, the visible surface of the sun. The temperature here drops to approximately 5,500 degrees Celsius, and the plasma becomes sparse enough for photons to escape without being constantly absorbed. It is from this thin layer, about 500 kilometers thick, that the light we see from the sun originates. Above the photosphere is the solar corona, which is itself an interesting environment, but its density is approximately 1/1000th that of the photosphere, and therefore not a significant impediment to a photon. It is amazing that an object like the sun, often called a ball of gas, can have such a distinct boundary. But it is in the photosphere that the photon breaks free, traveling at the speed of light, and begins its journey through the vastness of space. And the neutrino, born at the same time, has long since left the confines of the Milky Way. Since the sun entered its stable main sequence phase, nuclear fusion has steadily altered the star's internal structure, gradually increasing its luminosity over billions of years. This process is due to fusion inevitably leading to changes in the composition, density, and temperature of the sun's core, which in turn profoundly influences the overall behavior and future fate of our star. As hydrogen is converted into helium, the hydrogen reserves in the core are gradually depleted, and so-called helium ash begins to accumulate. Unlike hydrogen, which readily undergoes fusion reactions at the current temperatures in the sun's core, helium requires significantly higher temperatures to do so. As the concentration of helium increases, the core becomes denser. Helium nuclei have a greater mass than hydrogen nuclei, and as helium accumulates in the core, the overall density steadily increases. At the same time, because helium does not participate in fusion reactions and does not produce energy, it does not create outward radiation pressure to balance the sun's colossal gravitational pull. As a result, gravity begins to dominate, causing the core to compress further. To prevent collapse under its own gravity, the sun is forced to increase its core temperature as helium accumulates. A hotter core stimulates hydrogen fusion, as the rate of nuclear reactions is extremely sensitive to temperature changes. This increase in fusion intensity leads to the release of more energy, making the star brighter and temporarily restoring equilibrium between gravity and radiation pressure. Through this process, the sun's energy output has increased by approximately 30% during its existence, and this trend will continue for billions of years as long as hydrogen fusion dominates in the core. In the radiative zone, the layers become hotter and less transparent. The increased core temperature leads to the creation of more energetic photons, which are more likely to interact with and scatter off the surrounding plasma. As a result, this zone becomes less efficient at transferring energy outwards, trapping photons for longer periods before they can continue their journey. The convective zone has also expanded slightly over time due to the increased energy production. As the sun continues to burn its hydrogen fuel for the next 5 billion years, its core will eventually become overloaded with inert helium, which will no longer be able to sustain fusion under its own pressure. When this happens, the sun will transform into a red giant, expanding dramatically and engulfing its inner planets, including Mercury and Venus, and possibly even Earth. At this stage, the core will begin to contract and heat up until a helium flash occurs, and the fusion of helium into heavier elements such as carbon and oxygen begins once again, causing oscillations between the relentless gravitational pressure and the resisting forces of energy from the core. This process will lead to the formation of new layers and cause the sun to swell further before it sheds its outer layers, forming a ghostly remnant, a planetary nebula. The remaining core will cool and dim, becoming a white dwarf, a dense, Earth-sized ember of a once raging fire. Much of what happens inside the sun remains invisible to us, but its impact on our lives is no less significant. And yet, its influence on our lives is comprehensive and striking. If you were told that solar cycles could influence every aspect of your life, you might assume we were talking about astrology, not astronomy. And while many people believe in the possibility of predicting the future based on the position of stars and planets, the author usually does not subscribe to such a view, preferring to study the beauty of the cosmos and the mechanisms that explain its workings. However, even the most astonishing stories often hide a grain of truth. Based on the current state of the sun, it can be assumed that in 2025 you may face health problems, less reliable technologies, warmer weather with fewer clouds, and other unexpected consequences. How is this known? It turns out that the sun, this giant ball of fire in the sky, is not just a source of energy. Scientific research shows that its 11-year cycles can serve as a kind of metronome, determining the course of life on our planet. Life on our planet is subject to an inexorable rhythm, like a ticking clock. How is this possible? Let's delve into this astonishing phenomenon. The sun's influence on Earth is undeniable and multifaceted. This celestial giant is, in essence, the source of life. The energy necessary for the existence of all living things, in most cases, comes from it. The light that nourishes plants, which serve as food for herbivores, and they, in turn, become prey for predators. Such is the food chain, at the heart of which lies solar energy. It is difficult to imagine the existence of anything on Earth without the beneficial influence of our star. However, beyond bestowing life-giving energy, the sun is often perceived as a static object. We observe its sunrises and sunsets without noticing any significant changes. But this is nothing more than an illusion. The sun is in a state of continuous transformation. The sun is a seething, constantly changing mass of plasma, barely contained by gravitational forces. Nuclear reactions occurring in its core generate colossal temperatures, reaching 15 million degrees Celsius at the center. This monstrous heat causes the plasma to churn and erupt outward, forming solar flares that scatter in all directions. On the sun's surface, sunspots appear, drift, and disappear. Dark areas permeated by powerful magnetic fields, ranging in size from 1/600 to 160,000 kilometers. From the solar corona, the atmospheric zone surrounding the sun and having a temperature 200 times higher than its surface, coronal mass ejections occur. It is difficult to find a place in our planetary system more dynamic and active than the sun. Many do not realize that solar activity undergoes cyclical fluctuations. The sun operates according to an 11-year Schwabe cycle, during which periods of low activity, or solar minimum, are replaced by periods of increased activity, or solar maximum, and vice versa. During a solar maximum, the frequency of sunspots, flares, and coronal mass ejections increases significantly. The probability of a solar flare occurring during this period increases 50-fold compared to a solar minimum, and large coronal mass ejections occur not once every few days, but several times within a day. Curiously, the Schwabe cycle is only part of the larger Hale cycle, which reflects changes in the sun's magnetic polarity. Every 11 years, meaning during each Schwabe cycle, the sun's northern and southern magnetic poles swap places. After the completion of the next Schwabe cycle, the poles swap back. These continuous ebbs and flows of solar activity permeate our entire planetary system, like a pulsating heartbeat. And, surprisingly, we, the inhabitants of Earth, move in unison with this rhythm, though we may not realize it. The reasons for the cyclical nature of solar activity are not fully understood. It is clearly related to magnetic processes occurring deep within the sun. Despite scientists observing these cycles for the past 200 years and having data on their impact on Earth for the past 10,000 years, they still have not figured out why the solar cycle duration is exactly 11 years and not some other value. What force governs this process? In the absence of more convincing explanations, some researchers have tried to link the orbital period of Jupiter, which is also about 11 years, to the duration of the solar cycle. However, this could simply be a coincidence. Although Jupiter's mass is 2.5 times the combined mass of all other planets in the solar system, and it does exert some gravitational influence on the Sun, its orbit cannot explain the variations that the solar cycle undergoes. Many processes occurring within the Sun remain a mystery to us. However, its influence on Earth is much more apparent. First and foremost, this concerns outer space, which is becoming increasingly important for modern civilization. Therefore, it is not surprising that coronal mass ejections and solar storms regularly emanating from the Sun affect our technologies in space. Scientists can predict the approach of a solar storm, also known as a geomagnetic storm, days or even weeks before it reaches Earth. This allows astronauts to take shelter in safe havens to protect themselves from harmful increases in radiation levels, and also provides an opportunity to shut down sensitive equipment on satellites to prevent their failure. This is extremely important, as solar radiation can cause unpredictable electrical currents in wiring, leading to system overloads for systems not put into a safe standby mode. Safe standby mode is not the only aspect of geomagnetic storms that might surprise you. All this radiant energy affects the atmosphere, heating it, albeit slightly. As it heats up, the atmosphere expands, which impacts satellites. In space, there's virtually no drag, allowing objects to orbit almost indefinitely. However, this isn't entirely true. Satellites in low Earth orbit must use fuel approximately 4 times a year to adjust their position, as there is still a small amount of atmosphere present there. During a geomagnetic storm, the atmosphere expands, and low Earth orbit satellites must maneuver every 2 to 3 weeks to avoid falling due to increased drag. And even that is not always enough. In 1989, a geomagnetic storm so powerful occurred that it disabled a NASA satellite, the Solar Maximum mission, as the expanding atmosphere suddenly slowed its movement. Ironically, this spacecraft was studying solar flares, and this is not an isolated incident. The North American Aerospace Defense Command has to move hundreds of satellites after each geomagnetic storm as they deviate from their previous orbits. Radiation can also affect the ionosphere, filling it with charged plasma. This can cause a lensing effect in global positioning systems, reducing their accuracy from 1 meter to more than 10 meters. The next time your navigator shows you're not where you actually are, a geomagnetic storm might be to blame. Power systems prepare every 11 years for an increase in such current-inducing phenomena to avoid overloads. Radio amateurs and airline pilots, on the other hand, use these enhanced atmospheric conditions, bouncing signals off them, which significantly increases the range of high-frequency radio waves. However, for those not interested in amateur radio, all this leads to reduced technological reliability, and the fact that the next solar maximum has already begun makes this forecast quite likely. There are also upsides. As space weather turbulence increases, the frequency of auroras, mesmerizingly dancing in the night sky, increases in some regions of the world, such as Canada. Northern Lights hunters report an increase in sightings from several times a year to twice a month during periods of highest solar activity in the 11-year cycle. So we have examined the sun's influence on space and our technologies. It might seem that this is where it ends. The solar activity cycle affects technology, but does not significantly impact living organisms, right? But that's not the case. It's not for nothing that the horoscope mentioned declining health. There is growing evidence that solar cycles can even influence ecosystems and species themselves, including humans. Some of these phenomena are coincidental. When the Schwabe cycle is at a solar minimum, the sun exerts less pressure with its solar winds, which, ironically, means that the heliosphere provides less protection from cosmic radiation. This form of radiation is high energy, But fortunately, it rarely penetrates the atmosphere as it is absorbed or deflected by air molecules. However, even a small amount of radiation reaching the atmosphere is enough to manifest an effect. There is a theory that this additional radiation can create nucleation centers in the atmosphere, promoting the formation of more clouds, which affects weather patterns. Even if this is not the case, during a solar maximum, space weather affecting the atmosphere can slightly raise the global temperature. As the horoscope predicted, warming is occurring. The temperature increase is slight, less than half a degree Celsius, and eventually the temperature returns to its original level. But it is enough for temperature-sensitive species to notice and, for example, decide to begin their breeding season. Studies have shown that in warmer years, birds tend to lay eggs earlier. Interestingly, a study published in 2009 by scientists from the Netherlands showed that the timing of great tit egg laying also depended on the number of sunspots, which even researchers found difficult to explain. After all, birds cannot see sunspots. Nevertheless, a correlation appears to exist, according to data from the 5 nests studied. The influence of solar cycles is not limited to birds that navigate by magnetic fields, such as great tits or homing pigeons, whose routes change depending on the phase of the 11-year solar activity cycle. It extends to human health. Numerous studies investigate how solar cycles can affect human well-being. In 2011, a study covering 2 decades and almost 1/3 of the female population of the Netherlands was published. It revealed a surge in cervical pathologies that occurred immediately after a solar maximum, a period of the most intense solar radiation. The same study examined data from 1 male over the same period, which, of course, represents a much smaller sample. Nevertheless, a small increase in oral temperature, heart rate, blood pressure, and respiratory rate was noted shortly after the solar maximum. The influence of solar activity is not limited to physical health. It also affects mental well-being. A study conducted in 2006 analyzed 237,000 clients from the main Medicaid database, collected between 1995 and 2004. Scientists found that among these clients, those born during periods of high solar activity exhibited increased levels of mental disorders. Thus, the phase of the solar cycle at the time of a person's birth may have an impact on their later life. This is not exactly a horoscope, but there may be a grain of truth in astrology, at least concerning one particular star. It must be emphasized that scientific research in this area is still in its early stages, and any health consequences caused by solar cycles are extremely minor. According to one researcher, it took studying data from hundreds of thousands of patients to detect any health effects. Solar cycles should not be an impediment to living a full life. We are currently approaching a solar maximum, predicted to occur in 2025. However, for those who fear living or being born during a solar maximum, it's worth knowing that it's not all bad. Studies suggest that increased radiation can foster creativity and adaptability. Perhaps it was during one of these solar cycles 80,000 years ago that the human brain first underwent a mutation that gave it the capacity for abstract thought and consciousness. If this is indeed the case, if solar maximums gave us the means to perceive the universe, then we owe them a great deal. Without them, we would not be who we are. By now, it should be clear that despite significant knowledge about the sun, much remains a mystery to us. Paradoxically, the brightest object in our sky leaves us in the dark about many questions regarding its functioning. However, scientists are actively working to unravel these mysteries, using advanced equipment to do so. NASA and the European Space Agency have sent spacecraft to study the sun over the past decade. These missions have been the closest in the history of studying our star, allowing for direct interaction with its atmosphere. Why are we sending these probes to the sun? What are they doing there? What has already been discovered? And what makes each of these missions unique? Let's begin with NASA's contribution, the Parker Solar Probe. This probe was announced in 2009 and launched on August 12, 2018, aboard a Delta IV Heavy rocket. Over nearly 7 years, it has made 7 flybys of Venus, gradually tightening its orbit around the Sun. On December 24, 2024, it made its closest approach to the Sun, coming within about 6.16 million kilometers of its surface, placing it inside the solar corona, i.e., its atmosphere. While so close, the probe would experience conditions comparable to the searing heat of 500 suns simultaneously, with temperatures reaching 400 degrees Celsius, 2,500 degrees Fahrenheit. The spacecraft approached the sun 7 times closer than any other craft before it. At such temperatures, many components used in sensitive equipment would simply melt. To protect the spacecraft and all its equipment, it is outfitted with an 11-centimeter carbon composite shield capable of withstanding these extreme temperatures. The shield has a white reflective surface that helps minimize heat absorption. This shield is always pointed towards the sun, providing protection for the spacecraft in this harsh environment. Being at a significant distance from Earth and orbiting an extremely dangerous object, the spacecraft must be as autonomous as possible. Because the heat shield must always face the sun, for large portions of its orbit, it cannot point its antenna at Earth. During periods of no communication, it manages each sensor, controls data formatting, and archives high-resolution data until it can re-establish communication with Earth and transmit the collected information. The development of the European Space Agency's Solar Orbiter mission began in 2012, and after 8 years of intensive work, the spacecraft was launched into space on an Atlas V rocket on February 10, 2020. During its mission, Solar Orbiter also utilized gravity assist maneuvers near Venus and Earth. These flybys allowed the spacecraft to achieve its initial 180-day orbit around the Sun. Every 6 months, the spacecraft makes its closest approach to the Sun, coming within approximately 43 million kilometers. This is, of course, significantly farther than the Parker probe's trajectory, but even at this distance, temperatures can reach 500 degrees Celsius, as sunlight will be 13 times more intense than on Earth. Solar Orbiter is protected by a special heat shield consisting of layers of titanium foil approximately 40 centimeters thick. This shield is not as effective as the Parker probe's protection, but it is entirely sufficient to ensure the spacecraft's safety during its hazardous mission. The objectives of the Parker probe and the Solar Orbiter largely overlap. Both missions aim for a deeper study of the solar corona, solar winds, coronal mass ejections, the structure of the Sun's magnetic field, and the interrelationship of all these phenomena. The Sun's activity, manifested in particle emissions, is subject to constant fluctuations. Magnetic reconnection processes in the star's magnetic field can release colossal amounts of energy into the corona, leading to the ejection of millions of tons of charged particles into space as powerful eruptions. These phenomena, as mentioned, are known as coronal mass ejections, or CMEs. When CMEs reach Earth's magnetosphere, they cause so-called geomagnetic storms, the most powerful of which can have devastating consequences. To assess the scale of potential damage, we must look to the most significant such event in recorded history, the Carrington event. Between August 28 and September 8, 1859, an unusually large number of sunspots were observed in the same region on the Sun. On August 29th, southern auroras were sighted as far north as Queensland, Australia, signaling an impending solar storm. Shortly before noon on September 1st, amateur astronomers Richard Carrington, after whom the event was named, and Richard Hodgson independently witnessed and documented an exceptionally bright solar flare. Each prepared independent reports, which were subsequently published in scientific journals. The flare heralded a powerful coronal mass ejection that hurtled directly towards Earth, covering 150 million kilometers in just 17.6 hours, significantly exceeding the usual speed of CMEs. Typically, CMEs reach Earth in several days. It is believed that this high ejection speed was due to a previous CME, which may have caused the large-scale aurora event on August 29th, clearing a path for the Carrington event, much like a giant sliding stream. Thus, an unobstructed path was opened for the most powerful CME known to humanity. On September 1st and 2, 1859, the most powerful geomagnetic storm ever recorded erupted. Auroras were observed worldwide, particularly in the northern hemisphere, as far south as the Caribbean. Over the Rocky Mountains in the United States, the auroras were so bright that their greenish glow woke local gold miners, who, thinking it was morning, began preparing breakfast. It was reported that due to the extraordinary brightness of the aurora, residents of the northeastern U.S. could read newspapers. The aurora was visible in sub-Saharan African countries, in Monterey and Tampico in Mexico, in Queensland, Cuba, Hawaii, and even near the equator, such as in Colombia. This is unprecedented, as auroras are not typically observed at mid-latitudes. By September 3rd, the celestial aurora was recognized as the brightest and most spectacular ever observed. However, along with its beauty, this storm brought unexpected problems. One consequence of the geomagnetic storm was that electrically charged particles emitted by the sun caused voltage surges in telegraph systems across Europe and North America, leading to their failure and, in some cases, even electrocuting operators. Telegraph poles sparked due to the charged atmosphere. Notably, some telegraph operators managed to send and receive messages even after disconnecting power to their devices. The storm was comparable to an electromagnetic pulse covering an entire hemisphere, relatively harmless to humans, but extremely dangerous to electronics. The power of the 1859 CME was so immense that it compressed Earth's magnetic field to the very boundaries of its atmosphere. Since North America and Europe were facing the sun at that moment, these regions of the world were most affected by the initial impact of the CME's core. Recalling geomagnetic storms recorded since the 1850s, some were significant, but did not lead to catastrophic consequences. For example, in March 1989, a coronal mass ejection hit Earth, temporarily disabling satellites and silencing radio stations in Europe. In Quebec, Canada, power was cut for a full day. Some residents of the region, mistakenly believing they were under attack from the Soviet Union, mistook the glow in the sky for the result of nuclear bomb explosions. Fortunately, this solar storm, like many others, did not cause tangible and irreversible damage. Nowadays, a coronal mass ejection comparable to or even exceeding the Carrington event would have far more catastrophic consequences than in the 1800s. In those times, technology was just beginning to develop, whereas today, humanity is surrounded by numerous complex systems, including satellites, computers, telecommunication networks, and power plants, which could be severely damaged by such an event. Due to the vast reach of a solar storm, the impact would be felt over a wide area. Power grids and telecommunications with their long cable lines would be most vulnerable. Without proper protection, transformers and power grids could fail, leaving millions of people without electricity for an extended period. Replacing damaged transformers could take years, as they are often custom-made and not mass-produced. A power outage would make it impossible to store food in refrigerators, and disruptions to the transportation system caused by gas station shutdowns would complicate the delivery of new food supplies. Credit card payment systems would cease to function. Internet access would be impossible, computers would remain unpowered, and batteries would quickly drain. Radio and television stations would be disrupted, hospitals would face difficulties due to depleted fuel for backup generators. As a result, humanity would be completely cut off from the outside world. The modern world is so dependent on technology, and especially electricity, that there is a fear of losing the ability to function as a society if it is cut off. One only needs to recall the recent reaction to the temporary shutdown of TikTok in America. The most alarming fact is that the power system is most vulnerable to the impact of a supersolar storm. According to one independent think tank, the damage to the United States alone could amount to $2.6 trillion, leading to devastating economic consequences. Unfortunately, this estimate does not account for the social consequences that could arise. As is often the case during natural disasters, some people may exhibit their most primal instincts, operating on a every man for himself principle. Chaos, looting, and disregard for the law are possible. The situation would worsen as the population remains out of communication with the government or other authoritative organizations. It is hoped that kindness and humanity will prevail in such a situation, but a negative scenario cannot be ruled out. The think tank estimated the recovery period after damage from a coronal mass ejection to be 4 to 10 years. and suggested that during this time, up to 2/3 of the United States population could perish from starvation, disease, and chaos. Perhaps this sounds a bit grim, but when it comes to the sun, it's better to be aware of potential dangers than to hope they don't exist. Unfortunately, coronal mass ejections happen very quickly, reaching Earth in just 17 hours. This may not be enough time to warn the population, shut down nuclear reactors, and take necessary precautions. Until now, humanity has simply been lucky, as in July 2012, Earth narrowly avoided a collision with a coronal mass ejection comparable in power to the Carrington event. Had it occurred 9 days later, our planet would have been slightly further in its orbit and would have been in the path of the ejection. That is why it is so important for humanity, as a fragile species, to understand the processes occurring in the solar corona, to more accurately predict solar storms, receive timely warnings, and perhaps avoid damage associated with a direct hit from a coronal mass ejection comparable to the Carrington event. It is only a matter of time, not if. Now, these two research spacecraft may seem similar, and while many of their objectives overlap, each possesses unique characteristics. The Parker probe, like a brave diver, plunges deep into the solar corona, a region hitherto untouched by any man-made object. Due to the necessity of withstanding extreme temperatures, the design of this spacecraft has some limitations. For example, it cannot take direct images of the sun, as current camera technology does not allow them to survive such close and intense exposure to sunlight. Nevertheless, the Parker probe is equipped with instruments that enable it to directly sample and collect data on particles present in the solar corona, as well as to study in detail the regions where solar winds originate, which is impossible to do from a distance. The Parker probe is smaller, lighter, and carries less equipment compared to the solar orbiter. The solar orbiter, in contrast, carries both particle detectors and telescopes. It is capable of taking large-scale images of fascinating solar landscapes, and its orbit allows it to track regions of the solar atmosphere for much longer than is possible from Earth. This gives it the ability to observe the development of storms in the atmosphere over several days. Thus, these probes, like links in a chain, complement each other, and each makes its unique contribution to deepening our understanding of the solar corona. So, what progress have these missions made to date? As mentioned, on December 24, 2024, the Parker probe made a flyby 6.16 million kilometers from our star, setting a record for the closest approach by a spacecraft. Additionally, it became the fastest man-made object in history, reaching a speed of 692,000 kilometers per hour during its daring dive. Data transmitted by the Parker probe is already helping us understand the mechanisms of interaction between the sun's magnetic field and the corona that lead to the formation of solar winds. The probe also discovered that some of the sun's magnetic fields penetrate through the solar atmosphere, which can increase the speed of the solar wind by as much as 500,000 kilometers per hour. Furthermore, it found evidence of a dust-free zone at a distance of 5.6 million kilometers from the sun, which is thought to be related to the evaporation of cosmic dust particles under the influence of solar radiation. The solar orbiter has already transmitted its first images of the sun, in which scientists have discovered so-called campfires, small explosions on the sun's surface resulting from disturbances in small magnetic fields. The solar orbiter also took the closest ever pictures of the sun's surface from a distance of 77 million kilometers, and studying particles in its orbit will help us better understand different types of space weather. But perhaps one of the most astonishing discoveries by these probes was not what they saw, but what they heard, which raises the question, what does the sun sound like? This simple question seems to have a simple answer. The sun is silent. Since sound does not travel in a vacuum, to us, the sun sounds like nothing. But let's set aside simple answers. What if sound could actually travel in space? Without a giant cosmic mute button between us and our closest star, what would we hear? Would the sun sing to us a charming melody in our sky? Or would its noise be so catastrophic and cacophonous that it would be the last thing we ever heard? Scientists actually know the answer. With spacecraft like the Parker Solar Probe currently orbiting the Sun, they can detect the types of pressure and particle waves emitted by the Sun and can convert these waves into sounds we could hear if such transmission could exist in space. And, interestingly, not all sounds of the Sun are the same. And these sounds may allow scientists to unravel two of the Sun's greatest mysteries. In our imaginary scenario, where space suddenly acquired the ability to transmit sound, we can now begin to listen to the Sun directly from Earth. Although Earth is, on average, 152 million kilometers from the Sun, it is perhaps unsurprising to learn that the Sun is very loud, easily audible from where we are. It would sound something like this. It's important to remember that sound does not travel in outer space. The presented audio clips are the result of converting amplitudes and frequencies into sound waves, simulating how these waves might sound to human hearing if an atmosphere were present. This calming hum has a distinctive electrical quality, reminiscent of generators at work or even something vaguely radioactive, which is quite fitting given its origin from the Sun. Nuclear fusion, continuously occurring in the Sun's interior, generates 3.85 1026 watts of energy every second, which is approximately 1 million times humanity's annual energy output. This colossal power has a perfectly predictable effect on the loudness of the sound the Sun might produce. To visualize this, simply connect the device you are currently viewing this text on to a sound system used at a large-scale rock concert and turn this noise up to full volume. At 110 decibels, such a volume can only be tolerated for a short time, but prolonged exposure to such noise, continuously sounding in our sky, would likely lead to total deafness for Earth's population if people didn't use hearing protection. In reality, the lack of needing to deal with this is a huge stroke of luck. It's quite likely that living species would have evolved without hearing organs, as hearing would be useless in such conditions. As you approach the Sun's surface, the sound level increases exponentially, reaching, by some estimates, 270 decibels. It's important to remember that a decibel is a logarithmic unit, so an increase of every 10 decibels means a tenfold increase in sound level. To understand how loud this is, it should be noted that 270 decibels exceeds the limit that our atmosphere can physically transmit. There is a loudness limit of 190 decibels in Earth's atmosphere, as different mediums have different loudness limits. This is due to complex features of wave amplitude and energy levels, which we will not delve into. The Sun's loudness would exceed this limit by 100 million times. The Sun is an incredibly loud object. Unfortunately, some of the Sun's subtle sound nuances can only be distinguished when reaching this deafening zone. At the distance from which we perceive solar noise, many sound components merge, depriving us of the opportunity to hear some interesting details. For a deeper understanding of the Sun, it is necessary to approach it, entering this zone of incredibly intense noise. Therefore, for a moment, abstracting from the Sun's loudness, let's focus on its sound patterns. Imagine we embark on a space journey to the Sun. Soon, we will begin to notice changes in the uniformity of the sound. Instead of a continuous hum, we will hear something different, namely the sound of the solar wind. The Sun emits a continuous stream of charged particles that propagates throughout the solar system, and the nature of this phenomenon remains one of the greatest mysteries. At first glance, it might seem that this stream originates in the Sun's interior and erupts outward under the colossal energy of nuclear fusion. However, in the 1960s, an important discovery was made as a result of observations. It was found that although particles in the Sun's atmosphere, or corona, moved at an average speed of 145 meters per second, particles outside the corona moved at a speed of 618 meters per second. This meant that particles with sufficient speed to leave the Sun's surface drifted into space, and then some process in the solar corona accelerated them from subsonic to supersonic speeds, ejecting them. What exact process or mechanism is responsible for this still remains an unsolved mystery. The corona also holds another mystery. It has an excessively high temperature. It would be logical to assume that the Sun's center is its hottest part, and the temperature gradually decreases as you move away from the center. However, This ceases to be true when the corona is reached. The average temperature of the sun's surface is 5,500 degrees Celsius, but after just a few kilometers in the corona, the temperature suddenly skyrockets to 2 million degrees Celsius. Some process in the solar corona ejects the solar wind into space and also heats the surrounding environment to extreme temperatures. Scientists still do not know why this happens, although it is believed to be somehow related to magnetic fields. In this part of our journey through the vastness of space, we will likely encounter regions permeated by magnetic fields. It is here that we will experience the third sound of our tour around the sun. As our spacecraft approaches and crosses the boundary between the solar corona and the surrounding cosmic space, scientifically known as the Alfvén surface, we will be able to hear something special. These are the so-called Langmuir waves, generated by tiny oscillations of plasma particles vibrating under the influence of sunlight. These particles erupt from the sun through minuscule funnels on its surface, creating a magnetic phenomenon reminiscent of a boiling kettle. Imagine, we are entering one of these streams and countless similar streams are continuously erupting from the surface of our star. The outer shell of the sun is dotted with areas of hot matter rising from the star's interior, the so-called granules we mentioned earlier. Upon reaching the surface, this matter cools and sinks back into the star along the edges of the granules. In this process of matter rising and falling, or in some processes occurring within the sun itself, these descending regions eject powerful magnetic field lines. Plasma becomes trapped by the magnetic force and rushes into space, becoming the starting point of the solar wind. Scientists do not yet fully understand what causes this process, but the sound of Langmuir waves is truly mesmerizing in its beauty. As the solar wind moves, not all waves generated in this way propagate at the same speed. This leads to the dispersion of sounds, as faster parts of the wave overtake and slower parts fall behind, forming what are known as dispersive waves. These waves are filled with chirps, small sonic vortices where fast waves, catching up from behind, collide with slow waves already moving ahead. Eventually, this evens out into the hum we heard at the very beginning of our journey. But there's another sound that might shed light on this mystery, a sound with intriguing implications. Here, in the boiling solar corona, we can finally detect Whistler waves. Whistler waves are distant echoes of high-energy events propagating through the magnetospheric plasma of a celestial body. Similar phenomena occur on Earth. Every time thunder rumbles, we hear more than just the clap of thunder. Oscillations propagate through our planet's magnetosphere and can be detected many kilometers away if you have the necessary equipment. To truly appreciate the scale of these waves, let's listen to how they sound on Earth. Just a few short clicks and whistles, nothing special. Now listen to how they sound on the sun. The transition from rare short clicks to a cacophony of howling wind indicates that the sun's magnetosphere is not merely experiencing random lightning discharges. Something is happening continuously and ubiquitously, merging individual moments into a single continuous roar. Scientists are still trying to unravel the cause of this roar, but one theory explaining the force behind this sound and the dramatic acceleration and superheating of matter in the corona points to a subtle phenomenon known as magnetic reconnection. Magnetic reconnection sounds rather innocuous, but behind this innocent technical name lies a true cataclysm. The sun is a tightly twisted tangle of constantly changing magnetic field lines, all thanks to the churning plasma within it. Their power cannot be overstated. When magnetic field lines move away from the sun, they can sometimes merge with other field lines, forming the characteristic loops you've likely seen in images of the sun before. However, the moment such arcs form, true chaos begins. When two parallel lines touch, forming an arc, a large-scale rearrangement of the polarity of excess field lines occurs. Everything above the arc must find its place to maintain magnetic equilibrium. Freed from their bonds, the field lines further from the sun form their own arc, which is then catapulted into space like a giant stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to several million degrees Celsius in a matter of seconds. Quite recently, scientists have been able to observe nanoflares, but they are not yet entirely sure that the events they have recorded are truly the hypothetical phenomena they expected to see, although they apparently are accompanied by the supposed overheating. This explanation is still under development. Many aspects of this process remain not fully understood. Nevertheless, it does not seem too bold to suggest that it is precisely such moments, when the sun reaches the peak of its activity and seems to tear apart from within, that explain the high temperature of its corona, and why it ejects solar winds throughout the solar system with the power we observe. However, to go from a single click to the powerful hum we hear, and to explain the constant solar wind propagating in all directions from the sun, nanoflares, or whatever force is behind this phenomenon, must be extremely common throughout the solar corona. The sun continues to hold countless mysteries. The Parker Solar Probe, which helped gather many of these sounds, continues its journey around the sun, collecting valuable data with each new pass. Parker has almost completed its 7-year mission, but there is hope that it can gather even more information for scientists to carefully study. Perhaps they will have new sounds for us, each a key to unlocking an ancient mystery about how the universe works. Paradoxically, much like listening to the ticking of a clock to understand how the clockwork operates, the secrets of the sun may one day be revealed not by what we see, but by what we hear. Surely you believe that if we were able to orbit probes like Parker around our sun, then sending other objects to it should not be too difficult. Have you ever wondered if the sun could be the solution to some of Earth's waste disposal problems? Our planet faces a serious problem of environmental pollution. We're talking about plastic and other landfill waste, about what you throw away at home, and also hazardous industrial waste, such as nuclear waste, biohazards, and chemical toxins. All of this negatively impacts ecosystems and the health of vulnerable populations worldwide. At the moment, the best solution we've come up with for nuclear waste disposal is deep underground burial. This is far from ideal, considering these substances remain dangerously radioactive for tens of thousands of years. Why don't we just attach them to a rocket and send them straight into the sun, like a guided missile? Wouldn't that solve all our problems? To answer that question, it's worth noting that crashing anything into the sun is actually very difficult. Let's examine this in more detail. Suppose we collected a massive amount of toxic waste destined for the sun. The first thing we need to figure out is how to get it into space. This might seem straightforward, as we've been launching objects into space for half a century. To get our garbage package through the atmosphere and beyond Earth's orbit, we'd need to accelerate it to 11.2 kilometers per second. This speed, known as escape velocity, is the speed at which the payload's kinetic energy exceeds Earth's gravitational potential energy. Once our garbage craft leaves Earth's orbit, it will hurtle towards a collision with the sun, right? Not exactly. As soon as our package leaves Earth's orbit, it is still gravitationally bound to the sun. Simply put, Earth and everything on it is moving sideways relative to the sun at 30 kilometers per second. The combination of this sideways motion and the sun's gravitational pull is what keeps us in orbit. If the sun somehow lost its gravitational force, we would fly past it at 30 kilometers per second and continue our journey. If we on Earth lost our sideways motion, then only the sun's gravity would act on us and we would fall directly into it. So there's still hope for our garbage ball. How do we lose this sideways motion to achieve a solar freefall? There are two options. There are two possible ways to solve the problem of space debris disposal by sending it to the sun. The first option involves using a significant amount of fuel to decelerate the spacecraft in outer space. In the vacuum of space, strictly speaking, it is impossible to brake in the conventional sense. The most effective solution would be to equip the propulsion system of the spacecraft carrying the waste in such a way that it generates thrust in the direction opposite to its sideways motion. This would compensate for the sideways motion, reducing the spacecraft's speed and allowing the sun's gravity to do its work. Earth orbits the sun at 30 kilometers per second. Therefore, to brake a garbage rocket launched from Earth, it must be capable of accelerating by 30 kilometers per second in the direction opposite to its motion. Interestingly, as you approach the Sun, the task of colliding with it becomes more difficult. This is because the closer an object is to the Sun, the higher its orbital velocity. For example, Mercury orbits the Sun at a very high speed, reaching 48 kilometers per second, while Pluto moves much slower at only 4.7 kilometers per second. The higher the orbital velocity, the more deceleration is required for the object to begin free-falling into the Sun. For this reason, from a fuel efficiency perspective, it is more rational to fly into the outer solar system, where one can decelerate and then begin a freefall towards the Sun from there. Accelerating a spacecraft by 30 kilometers per second is a challenging but achievable task. As mentioned, NASA's Parker Solar Probe achieved a much greater speed, becoming the fastest man-made object in history. However, this brings us back to the issue of fuel. To implement the break and fall method, the garbage payload must first be launched into Earth orbit, and then the fuel needed for the onward journey must be delivered there. Once both parts are in Earth orbit, the payload can be fueled and accelerated to move beyond Earth orbit into an orbit around the Sun. Then, the remaining fuel would be used to decelerate the craft so that it begins to freefall into the Sun. The question arises, why not launch the payload and fuel simultaneously? The problem lies in the enormous amount of fuel required. For example, the Saturn V rocket, which took humans to the Moon, required 2 million liters of fuel just to leave Earth orbit at 11.2 kilometers per second. A mission to send garbage to the Sun would require orders of magnitude more fuel. No modern rocket technology is capable of delivering such a quantity of fuel in a single launch. So, the first scenario seems unlikely. What are the alternatives? Another way to decelerate in space is by using a gravity assist maneuver. Typically, when talking about gravity assists, we mean those used to send the Voyager probes into the outer solar system. However, gravity assists can be used not only to accelerate, but also to decelerate spacecraft. If a spacecraft approaches a planet from behind, flies in front of it, and then exits from behind the planet, it will lose some of its energy, while the planet gains energy. The Messenger and Bepi-Colombo probes successfully used this gravity assist technique to slow down and enter orbit around Mercury. However, it is worth noting that this process takes a significant amount of time. The Bepi-Colombo probe was launched in 2018 and will only reach orbit around Mercury in 2025. Surprisingly, its journey to Mercury is longer than the distance between Earth and Pluto. This is because one gravity assist maneuver is not enough to slow down sufficiently. The Bepi-Colombo probe needs to perform 9 different gravity assist maneuvers to slow down enough to enter Mercury's orbit. Similarly, sending garbage to the Sun requires precise calculations of orbital mechanics. If the deceleration is insufficient, the garbage will remain in orbit around the Sun. If the deceleration is too abrupt, the garbage may enter a different orbit that is not desired. In conclusion, sending garbage to the Sun is a complex but theoretically possible task. However, is it worth the time, effort, risk, and technical difficulties? Most likely, no. Potential risks and possible failures should be considered. What could go wrong if we sent garbage to the Sun? First and foremost, it is proposed to collect a huge amount of nuclear waste, biohazards, and plastic, put them in a rocket, and launch them beyond Earth. A failure or explosion at launch, to put it mildly, could result in a catastrophe of unimaginable scale. Even the most reliable rocket in the world, such as the Soyuz, has an estimated failure rate of 2 to 3%. And when it comes to nuclear waste, even such a small probability seems unacceptably high. Even if successfully launched, implementing such a project would cost an astronomical sum, so exorbitant that no sane person would approve such funding. There are many other scientific missions that would bring far greater benefits to science and humanity than a project to dispose of garbage in such an extravagant way. Ultimately, it would be simpler, faster, and cheaper, though still incredibly expensive, to send our waste beyond the solar system into interstellar space. This would require less fuel, as the speed needed to overcome the Sun's gravitational pull is 42.1 kilometers per second, which is only 12.1 kilometers per second more than Earth's orbital speed. So here's why we don't send garbage to the sun. It's incredibly difficult, carries enormous risk, and is tremendously expensive. We should probably be more responsible about what we consume and how we recycle waste. Returning to that quiet hill where this narrative began, where we watch the colors of the rising sun, it's worth noting that the sun is a majestic part of our solar system, vital to the existence of life on Earth. Let each sunrise be a special moment. May the pink and orange photons, scattering for the last time on Earth's atmospheric molecules before entering our eyes, make us ponder the incredible journey they have made, from the collapse of a colossal cosmic cloud into a melting pot creating elements and continuing their path through a plasma cauldron for hundreds of thousands of years to present us with this beautiful picture. May this realization deepen our appreciation for this daily miracle that we often take for granted, and there is still so much to learn about our closest star, from the transformations it will undergo to the profound impact it will have on the future of our solar system.